Hello everybody. So only 2 participants, right, today, Kathy and Rohan. Well, so we will start with a quiz. So it was online or offline, but now we should discuss the correct answers to this quiz. So the first question was, so the statement is there is a real 3×3 matrix with no real eigenvalues. Is it true or false? No real eigenvalues. So false. It's false, right? Let's explain. Let's justify the answer. Why is it false? Okay, because the characteristic polynomial P lambda, so PA of lambda is a cubic polynomial, the polynomial of degree 3, right? Cubic polynomial. So it looks like, so maybe it will be minus lambda cubed plus something else. So since the degree of this polynomial is odd, so this is an odd degree polynomial, then it must have a real root, right? So since there is a real root. And this root is proved to be a real eigenvalue. So it's false. I think it's clear.
Can you see the time you submitted the quiz?
So now it's time to submit it. No.
I submitted at 12:40 exactly, but Google actually is saying handed in.
So it's okay. So it doesn't matter. So if you are late, so if you are late in 1 minute or 2 minutes, the delay is 1 minute or 2 minutes or 3 minutes or even 3 minutes, it's okay, right? So don't worry about this. Next, task number 2. Every eigenvalue of a complex symmetric matrix is real. Any eigenvalue of a complex symmetric matrix is real. So is it true or not? So we have proved the similar statement, but for the Hermitian matrices. It's true for not for symmetric matrices, but for Hermitian matrices. Okay, so this is the explanation for task number 1, and for task number 2, 2 is true. So statement is true for Hermitian matrices. That is the matrices such that a conjugate transpose equals A. So it is true, but not for symmetric matrices. Not for symmetric matrices. For example, if we consider the matrix A, let it be 0, I 0. Let's consider this matrix. Then let's try to compute the eigenvalues of this matrix. To do this, we should first form the matrix A minus lambda I. It is minus lambda I minus lambda. And then find the determinant of this matrix, and this will be the characteristic polynomial. It is the determinant of this matrix, and it is equal lambda squared minus I squared. But I squared is -1, so it is equal to lambda squared plus 1. Okay. And the roots of this polynomial are both complex. It is equal to lambda plus I times lambda minus I. So then statement 2 is false. But it was difficult, I think. Rather difficult. Okay, what about number 3? So it's easy. Is this matrix Hermitian or not? What is your answer? No, of course not. False. Because for Hermitian matrices, we need this condition. So this condition should be satisfied for Hermitian matrices. But if we take the conjugate transpose to this matrix, we will get the matrix. So I need space. I will use this space. So 0i, I2 conjugate transpose will be, so we should take the transpose and take the conjugates of each elements of each entry, and so we will get this minus I and 2. So it is not the same as the original matrix. So it is not Hermitian. False is the correct answer. Next, the conjugate transpose of a unitary matrix is unitary. Conjugate transpose of a unitary matrix is unitary. So it's true. So I will need the space to explain this, so I will use this space. What is the definition of a unitary matrix? What is a unitary matrix? So U is unitary if U inverse equals U conjugate transpose. U inverse equals U conjugate transpose. This is the same as U inverse equals U conjugate transpose. So by definition. So let's consider the conjugate transpose to the matrix U, right? So what about, so U is unitary, then what about UH? Let's consider UH inverse. So I mean U conjugate transpose inverse. So we can change the order of these operations. So by the properties of conjugation, of transposition, and taking the inverse, so it is the same as U inverse and then conjugate transpose, right? So it is U inverse H. Well, and then it is equal to, so U inverse, so since U is unitary matrix, is a unitary matrix, then we have U inverse equals U Hermitian, U conjugate transpose. Then it is equal to U conjugate transpose. Okay, just a moment. So it is Hermitian, right? And it is U conjugate transpose. right? And it should be, I will wait. So I should see. So conjugate transpose, then we take the inverse, then we take the conjugate transpose. And what is HH, right? It should be okay, H. Right, so correct. And we can see that this, our new matrix W, call it W, we can see that W inverse is equal to W conjugate transpose, right? So this is W conjugate transpose. Well, so proved. So the answer for the task number 4 is true, it's true. It's true. And now let's discuss the last task. Okay, task number 5. There is at least one n by n matrix for which the characteristic polynomial of this matrix is equal to 0. Is it true or false? It is true. Because this is the statement of the, so this is a particular case of the, so not particular case, but let's, I'd like to recall the Kelly-Hamilton theorem. So Kelly-Hamilton theorem says that if A is any n by n matrix, then the characteristic polynomial of this matrix is always 0 for any n by n matrix. So there is not only one such a matrix, at least one matrix, but all n by n matrices satisfy this property. So this property is true for all n by n matrices by Kelly-Hamilton theorem. Well, so false, 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 true, and true. And the last task was to find the standard inner product of these two vectors, Z and W, where Z and W are two given vectors. So I will solve it. I will show the solution of this task. Okay, so by definition, so if I'd like to recall that if Z is the vector Z1 with components Z1, Z2, Z3, and Z4, and W is the vector W1, W2, W3, and W4, then the standard inner product, is defined by Z1 W conjugate plus Z2 W conjugate plus Z3 W3 conjugate plus the Z4 W4 conjugate. Okay, now let's use this formula. Okay,
The last one's true or false answer?
Okay, so they are true. So your answers are correct. So true and true, because number 5 is by Cayley-Hamilton's theorem. Not at least one matrix, but all the matrices satisfy this property. Okay, Ashish, so you are late, but maybe you may try to solve this task, and so I will give you points for this.
I've already submitted the task.
Right. So if you do it now, so I will give you points. So I don't want you to lose points, right? Because of delay. Right. Okay, the chalk is not very good. I will try to. I have my own chalk. Maybe it's better to use it. Okay, try this chalk. It's better. So 1 plus 2i times times. So you should multiply by not by 2 minus I, but what by what?
I,
Plus I, and so improve. So correct this. Minus I times 4 minus I. Then so it's minus 1, negative 1. Right. Minus I. Correct. Okay. Okay, right. So minus why minus 4i squared? So plus and plus, 2 pluses.
Oh, sorry. Plus 2.
So not minus 4 or plus 4i squared, or minus 4. Not both. So not plus 2i. So just a moment, I'll check. So 1 times 2, then 1 times I, it's this. 2i times 2 is, so without I squared, so 4i, and then plus 2i squared, right? And now it's correct. Minus I. Minus 4i plus I squared, correct. Minus 3, correct. To I. And now we should use the property that I squared. So since I squared equals negative 1, we can substitute this. And after this, we will collect similar terms. Right. Minus 3 plus 1 plus 2i. I. So 3i, correct. Minus 3. Correct. Thank you. Thank you, Ashish. So I hope it's clear. Please ask questions if you have any. And then we will go to our seminar. So these are tasks for you. Now I will clean this. Okay. Do we need a break, maybe? We may have a break now and next for 5 minutes and then continue. So is it time for a break? I think it's this. Okay, now we're ready to continue our seminar. And now we will try to solve the problems. So the first problems will be very easy. And so we should exercise with quadratic forms. And so by definition, a quadratic form it is denoted by Q, of the vector x, okay, can be represented as in matrix form as x, the vector x transpose times some symmetric matrix A times the vector x. A is a symmetric matrix, so this is so A is unique. It is uniquely defined by the quadratic form Q, and we can speak of the symmetric matrix. It is unique. And so the first task is to find the matrix A given the form Q. So 1A is this. Suppose Q is 5x squared plus 8xy minus 9y squared. And now our goal is to produce the matrix. So the matrix A will be, so 5 and 9 and negative 9 will go to the main diagonal. Right. Right. Welcome.
Which terminal are you answering the questions from? Do we have the paper, or is it uploaded on the drive?
Okay, so I have a paper, right? So, or
but it's not uploaded on the drive.
Ah, on the drive. So I will. I forgot. I have forgotten to upload the paper into the Google Drive, but I will do this. And now I will write the tasks on the board.
Okay. And where can we watch the recordings of this video?
The recording of this video will be available on the in YouTube. Okay. Right. So now A is formed. So 5 and negative 9 will go to the main diagonal. So 5 and negative 9. And then 8xy, we should split 8xy into the sum 4xy plus 4xy, because our matrix should be symmetric, and so it will be 4 and 4. So that's all. So this is the matrix. Okay, next, given so the more complicated quadratic form, let's consider the form, the following form: minus 3x1 squared plus 2x2 squared minus 5x3 squared minus 11 x1 x2 plus 4x2 x3 plus 12 x1 x3. Now the corresponding matrix, the associated matrix, will be, so these three coefficients will go to the main diagonal. So minus 3, 2, and negative 5. And then we should take this coefficient minus 11, x1, x2. So since it is multiplied by x1 and x2, we should find the entries, so 1, 2, and 2, 1 entries. 1, 2, and 2, 1 entries. They are here. Next, we should divide this coefficient by 2 and write to these positions, right? It should be, it must be minus 5.5 and minus 5.5. Done. Next goes 4x to x3. So divide by 2 and place in the position 2, 3 and 3, 2. So it will be 2 and 2. And then 12. So 6 and 6. And this is our matrix. Okay. Just a moment. So conversely, given a matrix, how to find a quadratic form? Let's do it. So, for example, so given a matrix A, which is equal to, for example, 1, minus 2, 0, 3, 3, let it be 1, 4, 4, and 1. So given this matrix, let's find the corresponding quadratic form. the quadratic form will be, so 1 will be multiplied by x1 squared. So x1 squared. Next, minus 2 will be multiplied by x2 squared. So minus 2 x2 squared. 0, so we can skip this, right? Next, 3 and 3 in the positions 1, 2 and 2, 1. So we should write plus 6 x1, x2. So we should double this coefficient and write in this way. So 4 and 4 in the positions 1, 3 and 3, 1. So it must be plus 8 x1, x3. And then plus 2 x2, x3. So we're done. This is the answer. Well, next, let's go to the next task. So now we will discuss positive definite and negative definite and indefinite quadratic forms. So these notions are very important. They will be used in calculus. So I will recall, so the lecture was recorded yesterday, so maybe I should recall some facts about definite quadratic forms. Definite quadratic forms. Okay, so the form Q is called positive definite. On the entire vector space Rn, right? If for any non-zero vector from Rn, we have the following: Q of x is greater than 0. Okay. So the example of a positive definite quadratic form is the standard inner product, for example, or the dot product. So if for any vector with components x1 and so on xn, we are trying to find the dot product with itself. So Q of x, if Q of x is defined as x dot x, or in matrix form it is x transpose times x. So the corresponding symmetric matrix is the identity matrix. Then it is equal to x1 squared plus x2 squared plus so on plus xn squared. And we can see that for any non-zero vector, the dot product is positive. So this is an example of a positive definite quadratic form, right? Well, next we can consider negative definite quadratic forms. We will consider negative definite quadratic forms. Okay, so this is part 1. So Q is a negative definite. If for any non-zero vector, so for any non-zero vector, I said that this, but I didn't write. Non-zero vector. We have Q of x is less than 0. Okay, okay, what are examples of negative definite quadratic forms? For example, if we consider this quadratic form and change the sign, right? So if we consider the U quadratic form, Q1, which is equal to minus Q, right? We consider dot product and consider the the negative of this. Then we can direct computations show that this new quadratic form Q1 will be negative for all non-zero vectors. Okay, negative definite, and 3 is indefinite. If there exists a non-zero vector, if there exists a vector x such that Q of x is negative, and there exists y in Rn such that Q of y is positive. Okay. So positive definite, negative definite, and indefinite. And to be more precise, we can associate with each quadratic form two indices, the positive index of inertia and negative index of inertia, right? So we can do it in the following way. Okay, so given a quadratic form which is equal to now x transpose times A times x, where A is a symmetric matrix, we may so we can reduce this symmetric matrix to a diagonal form. So there exists orthogonal matrix P such that, so it is orthogonal, so P inverse equals P transpose. Okay, so a symmetric matrix can be orthogonally diagonalizable. Okay, and then there exists orthogonal matrix P such that P inverse times A times P is a diagonal matrix. Okay, whose diagonal entries are eigenvalues of our symmetric matrix. Well, so since P inverse equals P transpose, then this equation can be rewritten in the form P transpose AP equals D, a diagonal matrix. And so if we, but now we need to use maybe, so let it be, so A equals, I will multiply by, so I need to write A as the product of matrices. Then A is equal to P transpose inverse times D times P transpose P inverse, and this is equal to PD P transpose. And then if we substitute this matrix here, we can rewrite our quadratic form as x transpose P dP transpose x. And then if we combine terms in this way, so it is P transpose x transpose D P transpose x. Okay, so now if we denote P transpose x by y, so this is a new vector, so we make a change of variables, right, described by this orthogonal matrix. Y's are new variables, and if we make change of variables, then in terms of new variables y, our quadratic form is described by a diagonal matrix. And this means that it doesn't contain cross terms, cross product terms. So this means that in terms of new variables, it is equal to y transpose dy. And so since D is a diagonal matrix with the eigenvalues on the main diagonal, so it is equal to lambda 1 y1 squared plus lambda 2 y2 squared plus so on plus lambda n yn squared. So it doesn't contain cross product terms. Okay. So we say that Q is diagonalized using the matrix P. Okay, and we can introduce the notion of positive and negative indices of inertia. So the number of positive eigenvalues counting the multiplicities is called the positive index of inertia. The number of negative eigenvalues is called the negative index of inertia. And so for positive definite quadratic form, the positive index of inertia is equal to n for positive definite, right? And the negative index of inertia is equal to 0. So if Q is positive definite, I will use this notation. Q is greater than 0. So and for negative definite, n plus is equal to 0 and n minus equals n. So if Q is negative definite. Okay, and now we will discuss Sylvester's criterion, how to determine the indices of inertia, or how can we determine whether the given quadratic form is positive definite, negative definite, or indefinite. This theorem was proved on the lecture, and so you will see the lecture, or maybe you have always watched the lecture. So if you watch the lecture, you will find the theorem there, but now we will use it. So now we will discuss Sylvester's criterion, and I will show you how to use it. Okay. Maybe I will use this part of the board. So is it okay? Right? Okay, so given a quadratic form, we want to determine whether it is positive definite, negative definite, or indefinite. To do this, we should first form the matrix, the associated matrix, and then we should find leading principal submatrices. So A1 is just the entry located in the upper left corner. So it's this matrix. This is the first leading principal submatrix. Next, A2 is obtained from our matrix by deleting the last rows and last columns except for the first two. So we should consider only the matrix formed by first two rows and first two columns of the given matrix A. So A2 will be A11, A12, so 1, 2 because asymmetric, and so is A2, right? A22, and so on. And the last leading principal minor will be, so AN, it is the same as the original matrix A. And then we can find the leading principal minors, the determinants of these matrices. So delta 1 is defined to be the determinant of A1, and it is equal to A11. Next, delta 2 is the determinant of A2, and so on. And delta n will be the determinant of AN. And the Sylvester's criterion is so tells the following. So if all the a quadratic form is positive definite if and only if all these determinants are positive, right? A quadratic form is negative definite if all that of if leading principal minus alternate in sign starting with the negative value. So negative, positive, and so on. And this means that the quadratic form is negative definite. So if and only if the so the negative and positive values alternate. Okay, and now using this criterion, we will try to answer the question whether the given quadratic form is positive definite or negative definite, or neither. Okay, well, so task number 2. So 2a. So given the matrix Q, minus 10 x1 x2 minus 4x1 x3 plus 2x2 x3 plus 4x1 plus 2x2 squared plus x3 squared. Let's check whether it is positive definite or negative definite. So do you want? Right, welcome. So it is very difficult to orthogonally diagonalize it, right? Because this is a very complicated problem, so it requires complicated computations because we need to form the matrix. It will be 3 by 3 matrix. Next, write the characteristic polynomial. It will be a cubic polynomial. Then find roots, and it is not easy usually, right, to find the roots of this polynomial, and so on, right? Or maybe it has roots, but maybe if they are not integer numbers, or maybe so it will be a problem, of course. But this criterion allows us to answer this question without diagonalizing this quadratic form, just by counting there, so computing the leading principal minus. Welcome. So first form the matrix. Form the matrix first. Well, correct. Minus 2, that, right? Minus 2 and minus 2. This corner. This corner, correct. Well. Delta 1. We may single out this leading principal submatrices there. So these matrices, right? Usually they are indicated using the vertical and horizontal rules. It is not necessary. Alternate starting with negative. Alternate starting with negative, and then the quadratic form is negative definite. Okay. Right. Minus 17. Use this space, I think. It's key. So y plus minus, right, correct. So the last row, you use the last row, right? I see. So expansion along the last row. So I'm giving the comments in order to, so because they can't hear you.
Oh, yes.
Mm-hmm. Mm-hmm. Well, mm-hmm. Mm-hmm. Right, correct. Mm-hmm. 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 Correct. Mm-hmm. Mm-hmm. -17, right? Mm-hmm. Okay, what is the conclusion? So positive, negative, negative.
Nothing.
Nothing, right? Neither. So no. Thank you. No positive. So neither positive nor nor negative definite. It is indefinite, right? It is indefinite. Well, and then maybe so you need examples of positive definite or negative definite. Or we may try to solve task number 4. Find the values of the parameter lambda for which the given quadratic form form is positive definite or negative definite. Okay, given a quadratic form which is equal to lambda x1 squared. So lambda is a parameter minus 4x1 x2 plus lambda plus 3 times x2 squared. So we will form the matrix. A will be lambda minus 2 lambda plus 3. And then delta 1. So these are leading principal submatrices. Lambda 1 is equal to lambda. And delta 2 is equal to lambda times lambda plus 3 minus 4. It is lambda squared plus 3 lambda minus 4. It has roots, so it can be factorized, right? So lambda minus 1 and lambda plus 4. Okay, now let's analyze this. Okay, so positive definite or negative definite. For positive definite, it is necessary, so greater than 0. So Q is positive definite. If delta 1 is greater than 0 and delta 2 is greater than 0. Q is negative definite. If delta 1 is less than 0 and delta 2 is greater than 0. So we can see that in both cases we need this. So delta 2 should be greater than 0. So we will start with delta 2. Right? So lambda minus 1 times lambda plus 4 is greater than 0. We will use sign analysis, right? So the roots are -4 and 1. This is a quadratic polynomial and it is greater than 0 on the intervals. So if lambda is greater than 1, it is positive, right? Positive, negative, positive, and then change the sign. So sign analysis, right? So it is positive if lambda from -infinity to -4, and the union with the interval from 1 to +infinity. Right. And now let's look at lambda 1. It is lambda. It is equal to lambda. Then so lambda, if lambda is greater than 0, so I will mark it here. So let it be 0. If lambda is greater than 0, then we can see that for these values of lambda, both leading principal minus are greater than 0, right? So lambda is greater than 0 and lambda is greater than 1, then positive definite. So if lambda is greater than 0, 1 plus infinity, then Q is positive definite. Next, if lambda is less than 0, then principal minus should alternate in sign, starting with negative. So we should be here, right? Less than -4, and if lambda is negative, then delta 1 is negative also. So if lambda is from negative infinity to -4, Q is negative definite. So this is the answer. I hope it's clear. Right?
Ma'am, what is the application?
Sorry, what is? Application. So the maybe the nearest application will be, so you will meet in calculus. So when you study functions of several variables. So what about calculus? Have you already discussed functions of several variables or not? Yes, and if you have a function of several variables, then sometimes you are asked to find extrema of this function, right? Local minima or local maxima now of the function of several variables. And you start with finding the stationary points. So you should find partial derivatives, and you should equate them to 0 and solve the corresponding system. So have you studied this? So have you discussed the problem of finding local extrema of functions of several variables? So, but you will do this. You will study them in what follows, and the first step is to find stationary points, and the second step is to analyze whether it is a local maximum point or a local minimum point or neither, or a saddle point. So a saddle point, so the neighborhood of a saddle point resemble the horse saddle, right? This way. And so to analyze this, so given a function, to answer the second question, whether it is local maximum or local minimum or neither, you will use the quadratic form which erased from the second differential. So second differential of the function of a function of several variables is a quadratic form in variables dx and dy, for example, or if there are several dx1, dx2, dx3, and so on. So it is a quadratic form. It can be considered as a quadratic form, right? And then you may use this machinery to answer the question whether it is whether this quadratic form is positive definite, negative definite, or indefinite. If the quadratic form is positive definite, then we have a local minimum point. If it is negative definite, then local maximum point. And if neither, then it is a saddle point. Also, this is the direct application of this theory. So it is very important. Right. Okay. So, but you will be told, so the theory, so I think Leonid Pankratov will explain you this, and so it will be clear, and you will use this. At task number 3. Okay, so this task is devoted for reducing the given quadratic form to the to the diagonal form. So it will be devoted to diagonalizing quadratic forms without finding orthogonal matrix, so eigenvalues, eigenvectors. Sometimes it is difficult to do this. So it is not difficult maybe for 2 by 2 matrices, but for matrices of order 3, 4, 5, it is difficult to find the characteristic polynomial, then find the roots, then find the eigenvectors. Well, so to simplify this process, we usually use the Lagranges method. So our change of variables, so the change of variables will not be described by an orthogonal matrix. So the matrix will be so any non-degenerate, non-singular matrix, any invertible matrix, right? But we will see. So after this, we will see how many. So the we will be able to find the positive index of inertia, the negative index of inertia, or we'll be able to answer the question whether this form is positive definite or negative definite or neither. So sometimes we need the the standard form without finding the orthogonal matrix, right? So for example, so 3a, the form is 25x1 squared plus 30x1 x2 plus 10x2 squared. So the Lagranges method consists of completing the squares. So we should step by step consider complete the squares. So now look at this quadratic form. You can see that we have 25 plus 30, and so it can be represented as 5x1 squared plus, so 30 is represented as 2 times 5x1, so we will use 5x1 from here, right? And then we should multiply, so to obtain 30 we must multiply this by 3x2. So you can see 5x1, so 5x1 here and 3x2 here, and then to complete the square we should add 3x2 squared. And but we have 10 to x2 squared. So we have one copy of x2 squared left, right? So we should represent 10 x2 squared as the sum of 2 terms. Then the first 3 terms form the square. So plus 3x2 squared and plus 2x2 squared. Okay, so and now if we set y2 to be equal to 5x1 plus 3x2, and then y2 is equal to x2. So this is a non-singular change of variables, right? So the matrix that describes this change of variables is non-singular. It is clear. Then in terms of new variables, our quadratic form will take place, will take form y1 squared plus y2 squared. Okay, this is the description of the method. So it is much more easier than to find the orthogonal matrix that diagonalize this quadratic form. Okay, and so now we will consider more complicated example, but I will use this part of the blackboard to recall some important formulas for squares. So we will need this formula: a plus b squared is equal to a squared plus 2ab plus b squared. We will use it in what follows, and a plus b plus c squared, which is equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. Okay, so using these formulas, we will try to solve the second task. So B, using the Lagranges method, so reduce the quadratic form to the sum or difference of squares. So Q is equal to x1 squared plus x2 squared plus 3x3 squared plus 2x1 x3 plus 2x2 x3. Okay, so we will start with x1, and the first step is to indicate all the terms in the sum containing x1. So it's this and this. After this, we should complete the square. So x1 squared, we should gather them together. And for the perfect square, we need to add x3 squared. Okay. So the remaining terms will be x2 squared. So this one. Next comes 3x3 squared. But we took one copy of x3 squared for our first term. So we should write 2x3 squared. And next plus 2x2 x3. So we will form the perfect square, right? Plus x3 squared. Okay. So on the first, the first step is completed. So the first perfect square is formed, and now the number of variables is equal to n minus 1. So this algorithm can be conducted for any number of variables, and on each step we should form the perfect square with one of the variables, and so the number of free variables on each stage should be so decreased by 1, right? So now we have just 2 variables, and we will continue completing the square. So x2, we have x2 squared plus 2x2 x3. To complete the square, we should add x3 squared, and we have x3 squared left, right? So we have the following: x1 plus x3 squared plus x2 plus x3 squared plus x3 squared, and it will be y1 squared plus y2 squared plus y3 squared, where y1 is equal to x1 plus x3, y2 is equal to x2 plus x3, and y3 is equal to x3. Okay, so well done. So this task is completed. Okay, now see, and maybe someone wants to exercise. So who wants to solve? Number C. It is equal to x1 squared. Follow. Oh, it was, sorry, Kathy. You want. Welcome. X2 squared plus 3x3 squared plus 2x1 x2 plus 2x1 x3 plus 4x2 x3. Okay. So we use this chalk. So it's, it's better. Well, so we will use the formula which contains three terms, a plus b plus c squared, right? So we need to add x2 squared, x3 squared, and plus x2, x3, right? Correct. Right. And so we will use parentheses to emphasize that. So this is the perfect square, right? Next, we may subtract them, these terms. We have added something, and we will subtract, right? Correct. You have your notation for this operation, right? Dotted lines.
Yes.
It helps to separate terms, right? I see. Well, so squared, x3 squared. You have forgotten, right? And then you should continue to complete the square with, so using the last two variables, x2 and x3. Sorry?
Can we add terms to make it perfect?
Add terms and subtract terms.
No,
Right.
Add something which is not there and then subtract from.
Right, of course, yes. So you may add these terms and then subtract them. Of course, yes. Right. Sometimes it is more convenient, maybe. Add and subtract and then compute, then collect similar terms. Right. Thank you. Thank you. Okay. Okay, so pay attention to the following. so the number of squares should be the same or maybe less than, but not exceed that the number of the original variables. So we have 3 variables, and so we have 3 squares or maybe less than 3, but not more than 3, because sometimes students confuse so the following. So this is the common mistake. For example, given the form, so let it be maybe 3x1 squared plus 2x1 x2 plus 2x2 squared. And what about the following solution? Let's consider this term, and let's let's combine terms. So to form the perfect square, I will add x1 squared plus x2 squared. So this will be the perfect square. But plus 2x1 squared and plus x2 squared. And I will get the following: x1 plus x2 squared plus 2x1 squared plus x2 squared. And so we have started with 2 variables and ended with 3 variables. And then y1 will be equal to x1 plus x2, y2 is equal to x1, and y3 is equal to x2. Is it correct? So this matrix is not a square matrix, and it is of course singular, so they are linearly dependent, right? So y2 plus y3 is equal to y1, so this is not a change of variables. So please do not confuse this method with this wrong method, right? So on each stage, the number of variables should be maybe the same or maybe less by 1, right? But not greater. Okay, and now we will solve the last task. So it will be the most complicated maybe among all the tasks, and this will be the last task. So we will finish with this. Okay, well, now 3D. Q is this 2x1 squared plus 9x2 squared plus 5x3 squared minus 12x1 x2 plus 4x1 x3 plus 6x2 x3. So, well, okay, so maybe Ashish, do you want? Try. Okay, I suggest to start with the following. So since 2 is not a perfect square, let's do the following. 2 will be here and then form the perfect square inside the parentheses, and then after all we may, so if we need only coefficients of 1 and -1, so we may normalize our change of variables, so multiply by √2 or divide by √2, so it's okay.
But then it will be in fraction. This x2 will be in fraction.
Right, you may start with x2, right?
No.
Maybe. So no, because we should start with the, so we should collect starting with x1 squared and minus 12 x1 x2.
Or only 2.
Right, on these 2, and then complete with the x2 multiplied by some coefficient, not start with this.
Okay.
Right? So plus, so it will be minus 6 x1 x2, right? Minus. And so we need to add 9, right? so write it 9x2. So no, 9x2 squared, because this will be the perfect square.
Yeah.
But we have 9x squared, but now we have 18x2 squared.
Minus.
So we should subtract. Let's write that. So let's subtract.
Yeah.
Minus. Right. Okay. So so why this 9x2 squared? I think. Why x1 x2
Yes.
plus 9x2 squared? But so now it's okay. Now 9x2 squared minus and minus and here x2 squared, right? X2 squared, correct. And so do not forget about them. Oh, sorry, it's 4x1 x3. So we need to add it here, right? So we should collect. So in the first parenthesis, we should collect all the terms containing x1. So we should do the following.
Can you just start from the beginning again?
Okay, so from the beginning, right?
Yes.
Okay, so it's just the beginning. So on the first stage, we should collect all the terms containing x1. So this one, and this one. So plus 4x1, x3. Then we should create the perfect square. So we should complete the square, right? 2, right. Thank you. It's 2x1, x3, because we should divide by 2. So it's 2 is the common factor, right?
Why is 9x squared in the bracket?
Because it is needed to complete this square.
Why can't we just do
Maybe okay.
a
So
plus b plus c whole square? It won't work because x1, x2, x2, x3, x1, x3 are there. So can't we make
so we will use this formula. Look here. So this formula, this one, right? If we have the square of the sum of 3 terms, then we need a squared, b squared, c squared, and so pairwise products multiplied by 2, right? And so in our case, okay, maybe I will explain it myself. Thank you, Ashish. So you may sit down. So I will explain it, right? So it's difficult, of course. So we should collect 3 terms. These 3 terms, right? Minus 6 because we divide by 2. Then plus 4x1 x3 will be plus 2x1 x3. Then I want to complete the square, and so I have a is equal to x1. So if we compare, if you compare this with the second formula on that part of the blackboard, so a is x1, then b will be what? So minus 6x1 x2 should be equal to 2ab. So b must be equal to minus 3x2. Then 2ab will be minus 6x1 x2. Clear? Next, c is equal to, so x1 and 2x1 x3. So it is equal to x3. Right. So to complete the square, we need, so a squared is here. This is a squared. This is a squared. This is 2ab, and this is 2ac. To complete this square, we need to add b squared. B squared is 9x2 squared. Then c squared is x3 squared. And then 2bc. What is 2bc? It is minus 6x2 x3. And this is a perfect square. Okay, so is it clear? Follow? All right. So this is a perfect square. Okay, now we need to subtract. So we have added this one, and this one, and we need to subtract them. Minus 18x2 squared minus 2x3 squared plus 12x2 x3, and we should rewrite these three terms. So plus 9x2 squared plus 5x3 squared plus 6x2 x3. Okay, so this is the perfect square, and so I will rewrite it in the following way: x1 minus 3x2 plus x3 squared. This will be y1, and then I will collect similar terms. So it will be minus 9x2 squared. Next, plus 3x3 squared and plus 18x2 x3. Okay, and I will form a perfect square from these terms. So it is equal to 2y1 squared. I don't want to rewrite all this expression. I will call it y1, and I will denote it by y1, and so, okay. So next, minus, let it be minus 9 times x2 squared minus 2x2 x3. So it goes from, so these two terms, they are collected here. And to complete the square, we need plus x3 squared. Okay, so next we should add 9x3 squared and plus 3x3 squared. Okay, it is equal to 2y1 squared minus 9 x2 minus x3 squared and plus 12x3 squared. Okay. And now it is equal to 2y1 squared minus 9y2 squared plus 12y3 squared, where y1 is equal to, so this long expression, x1 minus 3x2 plus x3. y2 is equal to x2 minus x3, and y3 is equal to x3. Okay, so this form has no cross-product terms, but sometimes we need to represent our quadratic form as the sum of difference of squares without multiplication by 2, 9, and 12, right? How to avoid these coefficients? To do this, we should make the following change of variables. So if we denote root 2 times y1 by z1, so let z1 be this variable, root 2 times y1, okay, equals root 2 times x1 minus 3x2 plus x3. Then if z2 be 3y2, 3 times x2 minus x3, and z3, so right, 2 root 3 y3, so it is 2 root 3 x3. Then our quadratic form will be represented as z1 squared minus z2 squared plus z3 squared. And the positive index of inertia will be equal to 2. So n plus is equal to 2. So the number of positive coefficients, 2. And the negative index of inertia is equal to 1. Okay. So we will stop here. So that's all. Thank you for your attention. Next time we will start the differential equations. So this will be there will be the first lecture on differential equations and the first seminar, right? And so in this room, in this class, it will be recorded. So there will be two classes, one lecture and one seminar, and they are available in YouTube. Thank you.